I guess we can just get started. So last time we were doing this problem here and something went wrong. And I looked at it and figured out what the problem is. The first problem is this word right here. And so that means that instead of coming out this way, it's actually going the opposite. The wind's blowing that way. The wind's coming from this area. So the wind's blowing down that way. So, wow, can't do very much. So it's like going this way. And so that means that it's just blowing the opposite direction of what I said. So that means that this is plus and this is minus. And then, so you're adding these two vectors together. Or the idea is to add that one and that one together. And I don't know what happened last time, but I added these two. Well, this is a minus, but I didn't subtract it. I actually added it. So that's actually correct. The two wrongs make a right in this kind of situation. But this one right here, so 50 minus 28.284 is 21.7167. And so basically do the same steps as that we did here, as we did over here, except this is 21.7167. And this is going to be also 21.7167. And so that means this is 116.9 is the magnitude. So that's the ground speed. The ground speed is that one. And then the angle, so over here, instead of the inverse tangent of 78 over that, it's going to be 21.716 over that, which gives us an angle of approximately 10.7, which means that when you take this one, you're going to get 79.3. Okay, and so that's the other answer right there, 79.3 degrees. That's not a zero. Okay. So great. Any questions on that? Any of the other questions about this section? This is 12.2.
I had one on the homework.
Yeah, had a question from the homework?
Yeah, for 12.2b, number 4. I don't know why I just got confused on this. I thought it was just that you add the vectors, the components separately.
Okay, so 12.2, number 4. Okay, let me look that up really quickly. Find the sum of the vectors. Okay, so yeah, you just add it together.
That's what I thought, but I got it wrong. Oh, never mind. It's because I didn't put in parentheses.
Oh, okay, yeah.
Okay,
it's kind of picky on the notation. Oh, this is on the B homework, isn't it? Okay.
Yeah, the B
I was even looking at the wrong problem.
Okay.
Yay.
Thank you.
No, yeah, great. Okay, great. Okay, let's go to let's go to 12.3. And so last time we were right here on we had just finished number 6. Okay, so here's number 7. And so these 3 points form a triangle, and we're supposed to find all the angles of the triangle with those given vertices. Okay. So we can draw a picture. It doesn't really matter how we draw the picture. But maybe we'll just like make it so that maybe we should make it so that it's kind of somewhat resembles reality. Okay, so here's 2, 0. Here's the point P, that's 2, 0. And here's Q, which is 0, 1. And then R is going to be over here at 4, 5. Okay, so there's R at 4, 5. And these 3 points form a triangle. And we're supposed to find all of the angles of the triangle. Okay, so now we know that, we know the formula, let's see here. We know this formula here, the cosine is u dot v over the magnitudes of u and v. So let's put that right up here. There, so this is what we're gonna shoot towards. Let's just, because this is like finding a whole bunch of angles, maybe we'll just find one angle. So let's find the R angle. Wait, the first one is RPQ. RPQ. Okay, so this angle here. Okay, we're gonna go for this angle here. And so what you do is you start from that point and you go to Q. That's one vector. And then you start from P and go to R, and that's another vector. Okay, so from P to Q, it's going to be this point minus that point. So that's going to be -2, 1. And then from P to R, it's going to be the R point minus the P point. Okay, so that's 4 minus 2, that's 2. And then 5 minus 0, that's 5. Okay, so that's the PR point. Okay, now you can consider this to be U and that to be V in this formula here. So the cosine of that angle is going to be the dot product of those two, which will be, maybe I'll write that down. So it's the dot product of PQ and PR, all divided by the length of PQ. Oops. And the length of PR. That's not a very good R. Okay, so the dot product is going to be -2 times 2, that's -4, plus 1 times 5, that's 5. And then the length is going to be the square root of 4 plus 1 times, and then this length is the square root of 4 plus 25. So that's 1 over the square root of 5 times the square root of 29. Whoa. And we're supposed to round it to the nearest degree. So you're going to take the inverse cosine of this, 1 over the square root of 5 times 29. So you just plug that into the calculator. And what's that?
1.487. How many decimals places?
Okay, I think you have it in radians. You should change your calculator to degrees.
Okay.
I know that's kind of like against everything that we. Yeah, that's like goes against everything that we feel like doing, but change it to degrees. So did anybody else get 85 degrees? 85.2. Or am I the only one? Are we the only ones doing it? So change it to degrees and then let me know what you get.
It works.
It works, okay. Thank you. So let's see here. So 85 degrees. Oh, you put it in Webassign and it gives you the right answer. Okay, that's even better. That's kind of a big angle. So that means that this is a pretty big angle. This is also going to be big, and this is going to be small, really small. Okay, we're supposed to find the other angles, but we're gonna cut it there and go on to the next problem. You guys can find the other ones later, or now, I guess. Okay, so this one right here, the next section, we're talking about orthogonal, parallel, or neither. Now, let me explain what orthogonal means. Orthogonal is sort of a generalization of perpendicular. Oops. Perpendicular. But it's like in vectors. So if you have vectors like we're dealing with that in R2 and R3 and stuff that you can visualize, then orthogonal is the same as perpendicular. But it's more generalized because there are situations where vectors can be other things. They can be like functions can be vectors, for example, and matrices can be vectors. There's a lot. You can carry this theory over to a lot of other situations. And orthogonal is in that situation is just going to mean that the dot product is equal to 0. Okay, so it's not. So it's yeah. So the dot product is 0. That's what orthogonal means. Okay, orthogonal means this. And if the dot product is 0, then remember the formula right here, where we have u dot v over the magnitude of u times the magnitude of v. If this is 0, then the angle is going to be 0, which means it's going to be 90 degrees or pi over 2. Okay. That is unless one of these is 0. But the other thing about orthogonal is both the vectors have to be non-zero. So each of these vectors cannot be the 0. Neither of these can be the 0 vector because that's just like cheating, because the dot product of 0 with vector with anything is just going to be 0. So, but you're not allowed to have the 0 vector to be orthogonal. It has to be non-zero. Okay, and then parallel is where the parallel is when they're pointing in the same direction. And so for parallel, the way that you can tell that they're parallel is if they're parallel, then they're pointing in the same direction, and the angle is going to be 0. So the way that you can tell is that you got u dot v over magnitude of u times the magnitude of v equals 1. So that's going to be 1. So that means that this and this have to be equal. But also what it means is that, so parallel also means that one vector is a multiple of the other vector. Okay, so let's look at number 8. We have some examples here. So part A, we have the two vectors 9, 6 and -4, 6. Okay, so are they orthogonal, parallel, or neither? So anybody want to take a guess at this? You say orthogonal? Did you say orthogonal?
Yeah, it's orthogonal.
Yeah, those are orthogonal. Because when you take the dot product, the dot product is going to be negative 36. That's 9 times negative 4. And then 6 times 6 is 36. So that's going to be 0. So that's going to be orthogonal. Okay, what about part B? Here we have these two vectors, 6, 5, negative 3, and 5, 1, negative 5. What does that look like? If you take the dot product, what do you get?
I think it's neither.
Yeah, because that's going to be, because the first one is 6 times 5, that's going to be 30, and then 5 times negative 5 is going to be minus a 5, and then you have minus 15. And that
15.
is, yeah, if you're feeling lazy, then you just say, ah, that's not 0. It's actually 10, but just say that's not 0. Okay, you don't necessarily have to calculate that out. So that's going to be neither. And then the next one is, oh, this is the IJK notation, but let's put it to this one. The next one is negative 8, 4, 12 versus 6, negative 3, 9, negative 9. Okay, so what do you think about this one? If you take the dot product, then all the terms are negative, 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 right? So that's not 0, right? But what else do you notice? Yeah, this is kind of tricky. Parallel is when one vector is a multiple of the other. So is that by chance what we have right here?
Yes.
Yeah, it is. So if you were to take this one and, like, let's say multiply by 1/4, so divide everything by 4, you'd get negative 2, 1, 3, right? And if you were to divide everything here by negative 1/3, you would also get negative 2, 1, 3. Okay, so these are parallel.
Well, that's cool.
Okay, so let's see. Whoa, it's tied. It's a 3-way tie between orthogonal. Orthogonal has 1, neither has 1, and parallel has 1. Okay, so tiebreaker time, part D. Okay, so here we have, I'm going to write it like this: 4i minus j plus 4j. And the other one is 5i plus 12j minus 2k. Wait, that's a k, not a j. Right there. Okay, so this one, is it
It's
okay, is it
orthogonal.
Orthogonal.
orthogonal? Orthogonal. Okay,
Yeah.
so if you take the dot product,
It's equal to 0.
the first two 20, and then the next one is minus 12, and then the last one is minus 8. That's orthogonal. Okay, so that's 0, and 0 is the first letter of orthogonal, so it's orthogonal. You guys will put that in there.
Yes.
Okay, let's go to the next problem, number 9. Okay, so here we have these two functions right here, or these two expressions, or whatever you want to call them, and or curves. They're equations of curves, and it says find the acute angles between the curves at their points of intersection. The angle between two curves is the angle between their tangent lines at the point of intersection. Give your answers in degrees, rounding to 1 decimal place. Okay, so these two, let's see, where are they gonna intersect? There.
At 0.
Yeah, they're gonna intersect at 0. And then also one other place they're going to intersect, and that is, so if this one's blue, then that graph's going to be like this, a parabola. Okay, and if this one's red, then that graph's going to be,
Does it intersect at 1 as well?
yeah,
Probably
so they'll intersect,
5 comma
they'll
1.
intersect here. Yes, yes, 1 comma 5.
Oh,
So when x is 1 and then y is 5, so they intersect there and there. Oh, 2 places? I thought I was just going to have to do 1 calculation, but no, it's 2. Okay. Okay. At 0, but 0 is like easy because look, what are the tangents at 0 for each of these? So we take the slope is the derivative, right? So that's the first thing we need to do. So dy dx for the first one is, what's the derivative of that?
Ten x.
Yeah, good. And then the derivative of this one?
15x squared.
Yes. Okay, so okay, let's do this. Organize it this way. So this one is the blue function. And this one's the red function. Okay. Okay, now I'll make a little chart here. So there's 2 places where they intersect, and that is at 0, right, and at 1. Okay, so the slope here is 0. And what's the slope here?
10.
At 1. Yes, good, that's 10. Okay, and then over here, for this function, the slope here is 0. And this one is
15.
15. Okay. So these 2 points, the vectors, the tangent vectors are the same. So that means that the angle is going to just be 0 or 0 degrees. Okay, so I'm going to put 0, but then there's going to be another. So that's the first one, 0. So that's going to be 0 comma something. Okay, here for the second one.
No, she's not here.
Okay. Okay, so for the second one, we need to come up with a vector that is tangent to here. So if you have a slope 10, okay, so if you have slope 10, then that means that you're right, that you go up by 10 as you go across by 1. So a vector that corresponds to that one could be 1, 10. Okay, because the slope is 10, that means, okay, so remember the slope is the change in y over the change in x. And so if you want to force, you can force it to be, okay, this vector here is 110. That means, so as this changes by 10, this changes by 1, and that's going to give you slope 10. Okay? And then for this one, that vector can be what? 115, right? Okay. So now we know that the cosine of the angle between them is going to be A dot B over the product of the magnitudes. Okay, so A dot B is going to be, okay, 1 times 1, that's 1, plus big number, 150. And then we're dividing by the square root of, for this one, it's 1 plus 100. And then this one is 1 plus, what is that, 225? Okay, and so the angle is the inverse cosine of 151 over the square root of 101 times 226. Okay, so I just put that in the calculator and make sure you're in degrees mode. Okay, so 151 divided by square root. Man, this is weird. This is really weird. I get 1.897. What's around to one decimal place? So that goes to 1.9. 1.9 degrees. Does that work? Whoa. Well, it works. Okay, so the answers are 0 and 1.9. Okay, so any questions about that?
So brothers, you first graphed it, find where they intersected, then took the slope, put it into a vector form, and then use the dot product to find where the angles were?
Yes. Yes, yes. There's this formula here. Usually this formula here.
Right.
And then that means just take the inverse cosine of whatever this is.
Awesome.
This first one was for the point 0. It's a little bit easier because the tangents are the same. The tangent lines are the same. Yeah. So yeah, use the slope. You can always just use the slope. It doesn't really matter where you are on the graph. Okay, so I'm not choosing 1 because I'm at the point, because I'm at x equals 1. I'm not choosing 1 because of that. I'm just choosing 2 numbers here. I'm just choosing, if you have this, let's say if your slope were, okay, so if your slope were, let's say, -3 over 5, then you could just use 5, -3 as the vector. Okay, or -5, 3. One of those two, depending on. Oh, wait a minute. One of those two will work. Probably one won't work. So one of those two, because they're pointing in opposite directions. Okay. So the thing is that you want to get. So the other thing you have to worry about is, like, if you have, this is one of your vectors, and so this is one of the lines. So if you have a line here, you got two vectors from that line. One of them pointing that direction, another one pointing the opposite direction. Okay, and so if you have, or let me look up like here, because if you have two lines that intersect like that, okay, then you either want to take this vector and that vector, or take this vector and that vector. Okay, because like if you were to take this vector and that vector, then it's going to give you this angle here. But you want the acute angle. You want the acute angle, which is this angle, which is the same as that one. So you got to take. So that's how you have to work things out. Okay. Okay. So number 10, there's this vector here, and we're supposed to find the direction cosines and direction angles of the vector. Okay, so what that means is this. So let me draw the axes here. So this is the z-axis, the y-axis, and here's the x-axis coming out right here, right? Okay, so you have it's 1 along the x-axis, because that's I, and then minus 4j, so that's minus 4 along the y-axis. Okay, so that kind of puts us back here. And then it's minus 2 on the z-axis. So that puts us down here, okay? So that kind of puts us there. And so this is the vector right here, roughly. Okay, so what we're supposed to find is what's the angle. So the first thing for part A, we're supposed to find cosine of alpha. Okay, so alpha is equal to the angle between the vector and the x-axis. Okay, so that's supposed to be this angle here between the vector and the x-axis is what we're supposed to find. Okay. Yeah, that's what we're supposed to find. Now, so the way that you can do that is, again, we use the same formula. And so let's call this vector v, okay? And for the x-axis, we can use this vector here for the x-axis, just 1, 0, 0. That'll be the x-axis, 1, 0, 0. Okay, so the cosine of alpha is going to be the angle v dot x bar x over the product of the magnitudes, like that. Okay, so let's see. So this vector dot product with that is what? Well, this is 0 here and here, so that makes things a little bit easier. So you don't have to worry about 1 times the 1 here. So that's just going to be 1. And then the magnitude of this vector is the square root of 1 squared plus 4 squared plus negative 2 squared, which is 4. And then this one is just 1. This is a unit vector. So that's 1 over the square root of 21. So that means that alpha is the cosine inverse of 1 over the square root of 21. Okay, and so we'll get that on the calculator. So that's 77.4. So it's supposed to round that to 77 degrees. Okay, so let me just check and make sure that's correct.
So, Brother Hurst,
Yeah.
is this only specific to when you're looking for alpha, or just the cosine
Yes.
of alpha?
Yeah. Oh, alpha. Oh, wait a minute. Okay, so the problem is asking for the cosine of alpha. Oops. So just a second. Okay, so this is the answer to the first part. And then this is the answer to the fourth part. Okay, so the first part and the fourth part. Okay, so that's the angle, and this is the cosine of the angle. Yeah, and so now for beta, cosine of beta, oops. We're going to use y, which is going to be 0, 1, 0. Okay, and then we have vy over the magnitudes of v and y. Okay, and then so beta is going to be the angle between this and the y-axis. That angle there. Okay, so that's going to be a -4 in the numerator. And the denominator is going to have the square root of, it's still going to have the square root of 20. It's still going to be square root of 21. And this angle is going to be more than 180 degrees. So take the cosine inverse of that. I get 151 degrees. And then for the last one, the cosine of gamma, that's for the z direction. So that's going to be the angle between this and the z axis, the positive z axis. And so if you do the same thing, you're just going to get a -2 up here. That's also going to be more than 21 degrees. So that's the answer to the second part. This is the answer to the third part. And then I get 116 degrees. So just take the inverse cosine of that, and you get about 116 degrees. Okay, great. Any other questions about this? Okay, let's move on to the next problem. Okay, number 11. Okay, so this one uses the next formulas, which are the scalar projection of u onto v. So note that the order of this is important. Okay, so the u, so the projecting one vector onto another. This is the vector that gets projected, projected onto the other one. Okay, and then also here, this is the vector that gets projected onto. Okay, and then the onto one is the subscript. Okay, the subscript. Okay, and that's really important. And this right here is the formula for the scalar projection, and this is, which I've always used this notation here, but the book uses this for some reason. And this is the projection onto the other vector. Okay, So what does this mean? This means this, okay? So if you have a vector v right here, and let's say you have a vector u right here. Okay, so they're pointing in, these are pointing in different directions. Essentially, if you could drop down vertically, then this vector here would be the projection. Of u onto v, okay? Now, you could also have a situation where v is like this, and u is coming out like that, in which case it would still drop down like that, and this would be, and your projection vector would be this one right here. Okay, so that's u, and that's v. And one interesting thing about this is that, well, the projection vector of v onto u is parallel let me see. The projection vector of u onto v is parallel to v. If you take the vector u and subtract the projection, you'll get something that's orthogonal to v. Okay, so don't worry too much about this yet. But basically, this vector here, because this projection of u onto v and this vector is going to add up to u, right? So u minus the projection is going to be this vector here. And so you can see this is going to be orthogonal to, it's perpendicular to the red, to v. This vector is perpendicular to that. Okay, so let's get to number 11. It says find the scalar and vector projections of b onto a. Okay, so the scalar projection of b onto a. So that would be this one right here. So we want the scalar projection. So the b goes there and the a goes there. So it's what you're going on to goes down here, and what you're there is there. Okay. Okay, so that's going to be according to the formula. Let's see. The b replaces the u, and the a replaces the v. So it's going to be b dot a over the magnitude of a. Okay, so what's b dot a? That's going to be the -5 times the 6, that's -30. And then plus 12 times 9 is what is 12 times 9? 108. Okay, and then down here you have the square root of the modulus of a, so that's going to be the square root of 5 squared plus 12 squared. Ooh, I know what that is. Okay, so it's this is going to be negative 78 over 13, right? Okay, so that's just negative 78 over 13.
-6.
Oh, really?
Yeah.
I can simplify that.
Yeah, it says -6.
Oh my goodness. Yeah. Yeah, I got it wrong on Webassign, and I was wondering, oh no. Okay. So now we go for the vector projection. Oh, wait a minute. How does that work? Oh no, I still got it wrong. Oh wait, it's positive 78. What am I doing? Okay, good. Positive 6 works. Okay. So now we go for the projection. So now you've already calculated the scalar, so we can just multiply by this. Or we could just go through the whole thing. I'm not really used to doing it just like this, but we could just go here. Let's do the whole thing, okay? Now let's go here. Okay, let's just go here. Let's use this one. So the projection of B onto A is equal to the scalar projection of B onto A times A over the magnitude of A. Okay, and let's see. So the scalar thing that's 6 already. And then A is this vector here. So that's -5, 12. And we already know this is 13, right? The length of A is 13. So it's basically 6 over 13 times -5, 12. And you can distribute the 6 over 13 in. So you get -30 over 13 and 72 over 13. Okay. So we go ahead and put it in vector form. Okay, so this is the answer to the second part right here. And once again, if let's see, if A were this vector here, this red one, and B were this blue one, then this right here would be the vector projection. Okay, and the scalar projection represents how many times this would go out. So actually this would, we're not gonna get into that. Okay, so let's see. Let's just do number 12. Find the scalar and vector projections of B onto A. So we're finding the scalar projection of B onto A. And again, that's gonna be B dot A over the magnitude of A. And let's see, what is B dot A? It's the same as A dot B, right? So that's 4 times 3, that's 12. And then 7 times -1, that's -7. And then -4, that's the number is 4. Whoa, that's just gonna be 1. Okay, and then the length of A is the square root of 16 plus 49 plus another 16. And then the numerator, we're just gonna have a 1. And then denominator, we have the square root of 30, 49
81.
and 30, 80. Whoa, 81. Whoa, that's just gonna be 1/9. Oh, I like, these numbers are being very nice to us. 1/9. And then the vector projection. Let's use this part of the formula, okay? Let's use the B dot A over A dot A times A. Okay, so B dot A, we already know that's 1. And then A dot A, that's just going to be 81. Because it's just going to be this without the square root, right? And then A is 4, 7, negative 4. Okay, so that's 4 over 81, 7 over 81, and negative 4 over 81. Okay, so let's check and see if that works. Remember to put the parentheses around it or the vector notation.
Again. The helicopter again.
So we'll put that in there.
Again.
Okay, then that brings us to number 13. And this is the last concept, and that is the concept of work. And so, you know, in general, work is equal to the force times the distance. Okay. Now, this is when you have the force that's like in the same direction as the movement. But sometimes you have force that's in a different direction. And so not all that force is actually is contributing to the moving force of the work, right? And so that's why we come with the dot product right here. So the work is the dot product of the force vector with the direction vector, or the distance vector, okay? So here we have a force that's 8, negative 6, 7, and it moves an object from here to here. So in the formula, this is the force vector. And then the distance vector, what you're going to do is you're going to start with well, what do you think you should do? What do you think the distance vector is going to be? We're going from this point to that point. So we're going from one point.
4.
We're going from one point to another point, right? So that's P and that's Q.
Is it not going to be 4, 8, and 18?
Yes, 4, 8, 18. Okay, so you see how I got that? It's 4 minus 0 is 4. 16 minus 8 is 8, and 22 minus 4 is 18. So that's the vector right there. So you're just going to take the dot product of those two. So that's 8 times 4. Plus, and then you have negative 6 times 8. And then you have 7 times 18. So 32 minus 48 plus, 18 times 4, 18 times 7, 126. Okay, so if you add those together,
110.
110.
Yeah.
Okay, let's see if that works. So that's 110 joules. Now, okay, that works. Okay, so in the strike problems, you always have to worry about the units, but I guess no units came up. Oh yes, it says the distance is measured in meters and the force is in newtons. So meters and newtons is consistent with joules. Okay, so let's look at number 14. A sled is pulled along a level path through the snow by a rope. A 30-pound force acting at an angle of 35 degrees above the horizontal moves the sled 50 feet. So here, if this is the sled right here, and you have a rope attached right there, and that rope is at an angle of 35 degrees. And so you have basically have your force going in that direction, right? And you want the sled to move forward by, 50 feet. Okay, so what's your distance vector going to be? Anyone want to take a guess at it?
Would it be 50 cosine 35? Oh, never mind.
No, so your sled's going to move
It's going to be 50,
forward
0,
50,
0.
yeah, 50, 0.
Oh, yeah.
We're just saying codimensional stuff. Okay, so 50, 0 is going to be your distance vector because that's just going forward 50 feet. Okay, now your force vector is going to be, so the magnitude of the force is 30 pounds, right? That's the magnitude. And if you were to split those up into the horizontal and the vertical component, what's the horizontal component?
30 cosine 35.
Perfect. That's great. And then your vertical component is 30 sine 35, but who really cares because you're going to take the dot product, right? And there's a 0 there, so that's just going to go away. Okay, so work is the force dot product with the distance. That's just going to be 50 times 30 cosine of 35 degrees. Okay, so let's go ahead and calculate that. And the units kind of all work out. So we're good on the units. So 50 times 30 times cosine of 35. Round to the nearest whole number.
It's 25.
Okay, so what do you guys get?
Negative.
Anybody get? You get negative? No.
Yeah, I still haven't changed my calculator to the degree thing. So.
Oh well. Oh well, that's okay.
1229.
1229. Yeah, that's what I got. And Webassign agrees. Okay, and okay, great. That's it for 12.3. So let's go to 12.4, and here we're gonna study the cross product. Okay, here's a few formulas that will come in later, but essentially the cross product is an operation between two vectors, and the result is another vector that is orthogonal to both. Okay, we'll talk a little bit more about that. Essentially, this is the formula right here,
Mason.
but
For
the cross product.
For the robot to charge and Ryan took it downstairs.
And this
Yeah,
only
just
works
sit down
for,
still. Take your time and relax.
Well, I want to go downstairs.
okay, so this only works when you have three-dimensional vectors, okay? The cross product between two vectors only works in 3 dimensions, okay? And so you have to have 3 components. It doesn't work when you have just R2, okay? So just 2 components. You have to have 3 components. And so this is the formula right here, but the way that you calculate it is using this determinant. That's typically how people will calculate it. So if you want to take the cross product of these 2 vectors, then you'd set them up in this determinant, ijk. So these represent the x direction, the y direction, and the z direction. and then you put this first one, you just put that across the second row. And then the second vector, you put that on the bottom row. Okay, now when I do a 3x3 determinants, I usually will copy down the first two columns over here. You guys familiar with this? Anybody familiar with this?
I've seen it, but totally forgot how to do it.
Yeah, okay, so there's this, and this. So those three, that's going to be, this one, if you multiply these together, that's 27i. And this is 0j, and this is 0k. So those together. And then you subtract. Okay, so it's these three that are in the forward direction. And then you subtract the three that are in the backwards direction. So there's that. So that's 3k. There's this, that's 0i, and then there's this, which is 18j. Okay? So in the end, it gives you 27i, and then you have a minus 18j, and then you have minus 3k, right? And so that is 27, negative 18, and negative 3. So let's see if that works. I think I still had it on the other assignment, so I have it'll take me a little while to put this in here. Okay, and then you're supposed to verify that they're orthogonal to both A and B. If you just put in zeros for the other two parts, then you'll get it correct. But then you're really supposed to take, okay, so what we're supposed to do is take the dot product of this vector with this one. And so if you multiply this first by, if you multiply this by 2, so if you take A cross B dot A, that would be this vector is 27, negative 18, negative 3, dot product with 2, 3, 0. Then you're going to get 27 times 2, that's 54. And then negative 18 times 3, that's negative 54. And then you have a 0 for the last one. So that turns out to be 0. And then if you go A cross B dot product with B, let's just eyeball it. So 1 times 27, that's 27, and then 0, that's make the second term 0. So 27 plus 0, and then 9 times negative 3, that's minus 27. So that's 27 minus 27, which is also going to be 0. Okay? So it's orthogonal to both of these vectors. Yeah, okay. So let's go to the next. And maybe I should tell you about, okay, so there's something, okay, I'll add something really quickly here. There is something called the, in regards to this, we're taking the cross product of any two vectors. There's something called the right hand rule. Okay, and what that means is, let's say you have a vector here and a vector here, and you're taking, let's say that's U and that's V. If you do U cross V, here, just a second. Okay, so if you go U cross V, then what you want to do is you want to the way to visualize this is to go from U to V. So imagine the angle that's going from U to V. And then take the fingers on your right hand and kind of trace it through that angle. Okay. If you trace it going from, if you trace your fingers from U to V, then your thumb is going to point upwards, right? And so U cross V is actually going to point out, is going to come up like that. Okay, and it's going to be orthogonal to both U and V, and it's going to point up this way. Okay, now if you go V cross U, if you take your fingers and you go from V to U, so go from V to U. Now, the only way you can do that is if you put your hand kind of upside down. It goes from V to U, your hand kind of is upside down, and your thumb is going to point downwards. Okay, so V cross U is going to be this vector here, and it'll also be orthogonal to both of these. Okay, and it will point in the exact opposite direction as U cross V. Okay, so what happens is U cross V is actually going to be the negative of V cross U. Okay, so if you reverse the order of the cross product, then you will flip the sign of the vector. The vector will be pointing in the exact opposite direction. Okay. So that's just an aside right there about the right-hand rule. Okay, so let's move on. We'll have more cross products to take. So number 2, we're supposed to take the cross product of these two. Ooh, look at that. There's variables in there. How exciting. Okay, so A cross B. Okay, so you're going to set up the determinant. And then the first row is going to be T, 4, 1 over T. And the second row is going to be T squared, T squared and 1. And then the first column goes down like that. And the first 3 is going to be 4i. So there's that. And then there's, looks like T squared times 1 over T, that's T, so plus TJ. And then this one's going to be plus T cubed K. Okay, and so that's the positive direction. Now the negative direction is these 3. So that's 4 T squared K, and then this one is plus Ti, and then this one is plus TJ. Okay, and so then so you have 4i minus Ti. So that's going to be 4 minus T in the I direction. And then you have TJ minus TJ. Oh, that's 0. Yay. And then you have T cubed K minus 4. So T cubed K minus 4T squared K. So you got that. And then you can put it in as 4 minus 4 minus T, 0, and T cubed minus 4T squared. Okay, so let's see if that works. And then if you take the dot product of this with this, then you're going to get 4. Well, Okay, so A cross B, dot product with A. That's going to be T times that, so that's going to be T times 4 minus T, plus 0, because there's a 0 right there, and then plus 1 times that. Wait, no, plus 1 over T times that. So divide everything here by T. That's T squared minus 4T. And then everything reduces to 0. Everything cancels out. And then likewise, if you take A cross B, dot product with B, then it's this one times all that. So that's going to be T squared times 4 minus T plus 0. And then this other one's going to be 1 times that. So that's T cubed minus 4T squared. And that also adds up to 0. Okay. Number 3 says find the vector not with determinants, but by using properties of cross products. Okay, the cross product was invented by perhaps the greatest Irish mathematician ever, or the one with for sure the one with the most notable accomplishments in the field of mathematics. And his name was Hamilton. I forget his first name. Okay, Hamilton. And he also invented something called quaternions. But maybe one of the ways to look at this is if you have an I and a J and a K, and kind of think it as a circle going, kind of think of these as going clockwise. Okay, so if you take I cross J, you're going to get K. Okay, so if you're going this way, I cross J, you're going to get K. Or if you take K cross I, you're going to get J. Or if you take J cross K, you're going to get the next one, okay? Okay, that's if you're going in this direction. If you go in the opposite direction, so let's say you do J cross I, if you're going backwards, then you're going to get negative K. Okay, and if you go I cross K, then you're going to get negative J. Okay, so if you're going in the opposite direction, then you're going to get so K cross J, then you're going to get the next one with negative. Okay, and then quaternions work this exact same way. This is exactly how quaternions work. And they've got I, J's, and K's. Okay, so number 3, we have this expression right here. Distribution works on these. So you have this subtraction right here. This is actually going to be equal to K cross I minus, and then you have this 4 here, and that's K cross J. Or it's actually 4 cross, or it's actually K cross negative 4J, but the negative 4 can come all the way out right here. So you get that. So, and then K cross I, that's going in the positive direction, so that's going to give you J. And then K cross J, that's going backwards, right? K cross J, so that's going to give you actually negative I. So you get, what is this? 4I plus J. Okay, which you can also write as 4, 1, 0, I suppose. Okay, that works. Dang, I didn't want to accept this one. I think I have to do something more to it. because those are bold-faced ij's and k's, not just regular ij's and k's. So you probably have to do something to make it work. Okay, so that's number 3. Number 4. This is more of kind of the same. We already talked about that it's orthogonal to both vectors, and the direction is determined by the right-hand rule. Okay, so number 4. Okay, so we're running low on time, so let's just do number 4, and then we'll call it a day. So here, for number 4, we have it has a picture with the coordinate axis. Okay, the x, y, and z axis. And then it has B pointing up straight along here. And it has A coming out right there. Okay, and these, it looks like A is in the XY plane. Yeah, I'm going to go and say A is in the XY plane. It says A is in the XY plane. Okay, good. And B is in the direction of K. That means that these are orthogonal to each other. And there's this formula right here that A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. Here the sine is 90 degrees, or pi over 2. And so the sine is, and we know this is 3, that's 2, right? And the sine of 90 is what? It's just 1. Okay, so the answer to the first part is 6. Okay, so now for the second part, it says use the right-hand rule to decide whether the components of A cross B are positive, negative, or 0. So the right-hand rule, so if we're taking A cross B, so go from A to B. As you go from A to B, if you kind of stick your fingers there, then let's see here. Okay. Dang it. This is kind of a challenge. So is it going to point out, as you take your fingers from here to here, it's kind of in a weird angle. I'm trying to figure out how to. So the question is the vector going to point off this way, or is it going to point off that way? Yeah, it's going to point out this way, because if you curl your fingers from here to here, then your thumb's going to be pointing out this way. Okay, so it's going to be pointing this way, and so the x component is going to be positive because it's kind of pointing in the same direction, and the y component is going to be negative because because this is the negative y direction over here, and that's kind of this is going to push it that way, and then the z component is going to be 0 because it's got to be orthogonal to this, and so that means that it's got to be 0. It's going to be actually and also in the xy plane.